Hey there folks, Mr. G here with another educational video. This one we're going to be talking a little bit about the history and the development of atomic theory. Now last time we talked a little bit about how we know that matter is made up of atoms, and we mentioned Brownian motion as well as the electron tunneling microscope for some of the evidence for that. But we didn't really talk about the different ways that our understanding of the atom changed over time. So we have known for a while that the atom has existed, but we didn't necessarily know exactly what was going on inside of the atom. And our development of what we know about what the atom does has really changed a lot over time. And I just want to give you a quick overview of some of the key dates and key events, key changes that happened in the development here. Before we get started though, make sure you write down the date, and this is page number 6 of the notes for this unit. So starting all the way back in 400 BC, so that's over 2,000 years ago, there was a person named Democritus who was thinking a lot about what things were made out of. So what was the fundamental building blocks of the universe? And he thought that the universe was made up of something he called atomos, or atoms, something that was indivisible. So his idea was that if you cut something apart, smaller and smaller and smaller, eventually you'll get to a small piece that you can't cut anymore. And he thought that these atomos, these little atoms, had different types. So for instance, fire had a type of atom that were yellow, light, and very sharp. Rock atoms were hard and hooked together, things like that. This wasn't really based on any science, but this was based on philosophy. Now this is important though, because this is where we get the word atom from. Atomos, that's Greek for indivisible. Now fast forward almost 2,000 years to 1803. We have Dalton doing chemical reactions with gases, and he discovered that the atom chemical reactions happen when atoms rearrange. So elements always combine to form compounds in whole number ratios. So basically he figured out that chemical compounds, you always got these atoms combining together, different types of elements, and there's always kind of a certain number of each type. So you might have, for instance, in water, we have 2 hydrogens, 1 oxygen, and he figured out that that's true for all different types of gases that you combine together, that your elements always combine in whole number ratios. So 2 hydrogen atoms for every 1 oxygen. And he proposed the atom looks like a billiard ball. So for anyone here who's played pool before, the pool, the game, he imagined these as spherical balls that were really solid, and that's what made up an atom. Now they might be different sizes, but this is what he figured they would look like. Fast forward 100 years, Thomson did a cathode ray tube experiment, and he discovered the electron. He found that cathode rays bend towards positive charges, so they must be made of negative particles that are smaller than atoms. So he was in this cathode ray basically shooting rays of electrons, and he found they bent towards positive charges. So there must be something, and he got these rays off of atoms themselves. So he's able to strip the electrons away from atoms and shoot them in a beam, and found that they were negative. So what he said was, oh, that must mean that our atom is made up of a large positive sort of background with a bunch of little negative things inside of it. And this is called our blueberry muffin, where the background is the positive muffin, and then the little electrons here, those are our blueberries. Rutherford, he did an experiment shooting alpha particles, which is a type of particle, at a thin piece of gold foil, and what he discovered is that there is a center part, a nucleus made up with protons. And based on his experiment, he found that when he shot these particles, that sometimes they bounced off of something in the middle that must be really dense and really positive. So he discovered that the center of the atom has to be a dense, positively charged object in order for it to explain how the alpha particles bounced off of it. So by shooting alpha particles at basically atoms of gold, he found out that there must be a central region that is really small and positive. In 1913, a scientist named Bohr found that different atoms had different colors of light that they gave off, in particular hydrogen. So he discovered something called electron energy shells. So hydrogen only gives off a few colors of light. So if you heat up hydrogen, you'll notice that it only gives off certain colors of light. So what he concluded was that that means that each of these electrons has to have specific energies, and that's what's responsible for the light that's coming off. So instead of just these electrons kind of buzzing around randomly, they must be at really set energies. And if you remember from last time, the out ones have high energy, and the inner ones have low energy. And depending on what type of electrons they are, it'll give off a different color of light. Rutherford and another scientist named Chadwick built on this, and they found that you could actually take this positive center region that Rutherford discovered and break it apart even further, and they discovered the neutron. And they found out that based on their breaking apart, the nucleus had too much mass to be only made of protons. So there had to be some other neutral particles to beef up the mass without changing the charge. So it looks very similar to this model from Bohr from before, except for now there are little neutrons inside of it, in addition to our protons. Finally, Schrodinger and Heisenberg, using some very complicated math, figured out using quantum mechanics that electrons have to travel like waves, and they trace out these complex shapes. So it's not circles like this, but rather they have these kind of weird bubbles of probability. And so they came up with the idea of the Schrodinger wave equation, the Heisenberg uncertainty principle. Basically, instead of the electrons circling around nicely like this, they kind of float around in these probability regions where we don't really know exactly where they are, but we know that they have to exist in some certain area with some certain probability. This is super weird, and this is the sort of thing that you really don't dive into a lot of detail until you reach university physics. But this is something I spent a lot of time studying, and if you're interested in learning more about how this is possible and what quantum mechanics is, come talk to me. I'd love to tell you more about it, and maybe I'll post some cool videos about this as well. Finally, after understanding the atom at this level using quantum mechanics, we found that even protons and neutrons can be broken up further. So we have used particle accelerators to collide particles and break them apart, to break apart our protons and neutrons into even smaller pieces. Those are our elementary particles that we talked about last time. And when an atom breaks apart, when we smash it together with other atoms using our particle accelerators, which basically is taking these atoms, whipping them up to really, really high speeds and then smashing them together so that all of their little pieces fly apart, we can detect these tiny particles having different masses, different charges, and that gave us that big list that we saw last time. So for instance here, we have some pictures of a down and two up quarks, two downs and one up quark. And so these would be our proton and our neutron. And if we go back to the notes last time, we see that protons are the 2 up, 1 down. Neutrons are 1 up, 2 down. So this would be our proton, this would be our neutron. The important thing about atomic theory is that it is constantly changing. So throughout history, scientists made different observations that their models couldn't explain, and when an old model failed, they had to make a new one. And they're always working with other scientists. You'll notice how this picture is slowly evolving and that lots of people were involved. And there were even more people involved that didn't get named on this list here. Hundreds, even thousands of scientists. The current quantum cloud model of the atom is pretty good, but new big questions could arise that maybe this model doesn't do a good job of explaining. And we still use the Bohr model, these simpler models, to describe atoms because it does a good job of explaining a lot of things, including chemical reactions. So these simpler models, even though they're not perfect, are oftentimes good enough in really simple situations. If you're doing high school chemistry, the Bohr model is more than enough. You don't need the quantum electron cloud model. And in fact, this model is so complicated that if we insisted on using this, we probably wouldn't be able to do high school level physics, high school level chemistry very well. That's the end of our video here. The key point of this is to show you that science is developing over time and show you kind of how we got all of these different pieces here. If you're interested into more detail about the different experiments that were done and all of this, I'll maybe post a few videos. There's more resources in the textbook if you're really interested in diving into all of the details here. But that's the end of our video. Make sure you check Teams for homework, assignments, and anything else you got to do for today, and I will see you all in the next video.